Watch. So the last one, what tools do you use? For the 50% of you bothered to answer, this is what you said. So R was up there at 49%, Python 28%, etc. Excel 9%, SAS 16%. So we thought we'd have a talk on that. So without any further ado, we're going to introduce our first speaker, who's in the blue corner, Andrew Robinson. Now, was anyone here at the Christmas gala? Okay, no. Andrew was wearing shorts at that event, so you might not recognise him, but once he starts shouting, I think you'll remember him. So, Andrew, thanks for... I'll introduce him. I kind of googled Andrew and he said he's written all books in R. He's done a book on forests, is that right? Which I thought, random forests, he must be really into his pretty, but no, it was actually a book on forests, which he might tell you about. So, thank you. Andrew, cheers.
Thank you very much. Just so that there's no ambiguity.
He's going to shout again.
Can you send us off?
The volume there.
Off. It's going to give me the shits. Thank you. Seamless transition. So, they don't have a gong today. They promised that they wouldn't unnecessarily or unnaturally truncate my time, so I'm going to have my wicked way with you all. My goal is to spend some time talking about the ways that R makes me happy. The many ways that R makes me happy. I'm not going to make this, okay, it's going to be a little bit of a hagiography because I am a little bit of an R nut. And consequently, when I hear about other languages, my default reaction is to say, well, that's fine for somebody else, but I could do all this in R. But I'm a realist, right? I'm a realist, and I know that's not necessarily true, so I'm looking forward to Chris proving me wrong. But I'm going to preemptively prove him wrong too. So as I say, my goal is to just tell you about some things, some happy times when R made me happy. We're going to start with R, and then we're going to talk about not R. And then we're going to refresh ourselves as to what was the question. Okay, so R. Hands up here, who uses R? Don't be afraid, I'm not going to ask you any questions. That's great! You're my people. Hands up here who has never used R. Never used R. My dear friends, come up the front. We're going to have a group hug! You know what? Well, so R is... Oh, I have slides. I need to, in order to stay on time, I have to stay on slide. Because if I slide off my slide, then bad things will happen. And we'll still be here at 10. So here are some good points about R. R runs on Windows, Mac OS, and Unix alikes. It provides... I didn't tell you what it is yet. R is a statistical environment that comes with a language. So R is both a language and an interpreter of that language. A software interpreter of that language. It's mostly an interpreted language, so you can type R commands in at the prompt and you can get a response. I had this idea that maybe I should watch some Steve Jobs presentations before I did this, so I could say, well, just one more thing. Or I could say, this is the most beautiful, incredible device ever in the history of the world. But what I do want to say is, just as a little footnote, you can get R on your iPhone. You can because there's a message app on the iPhone, and someone has set up the R interpreter as a listener. So you can type R commands in, and a computer in Europe will return the answers, which I find oddly satisfying. I mean, I've got a laptop, right? The laptop's got R on it, but oh no, I'm there on the train going, I'm just going to type this little R thing in here on my phone just because I can. So R runs everywhere now. It provides many useful statistical and analytical tools, many of which have been tested. There's a caveat we'll come back to there. It produces publication quality graphics. When I say publication, I guess I don't mean the super fancy, super glossy stuff that you guys might be familiar with. I mean the more modest bar of academic graphics, which are actually still, that's a high bar, but it's not super high. I mean, we don't do 3D pie charts, for example. I know that you guys are devoted to that. R plays nicely with LaTeX via the SWeave package, and there are other ways of doing it as well. Run old school. SWeave is the way for me. It speaks CSV, FWF, which I really just want to say woof, SQL, HTML, and Markdown. It plays with nicely with Fortran and C and shell scripts. R is besties with C++. C++ and R are like this. I'll show you some of that later. R speaks your shell. It can seg, it can awk, R can grep. R scales, so you can use it on your phone to find out just what is the 95th quantile of the chi-square distribution with 5 degrees of freedom on the train. R celebrates the command line. If you're a command line kind of a person, R is good for you. Now, honestly, first caveat, I know that Python does most of that as well. Okay, so let's just put that aside. Okay, Chris, you win. R, however, encourages good statistical thinking. R is a language, and we use the language to formulate thoughts and to express them. And there are languages that are more efficient for certain kinds of thinking and less efficient for other kinds of thinking. And those of you who are bilingual in human language will understand that sometimes it's just easier to say things in French than it is to say them in English. Okay, well that's a testable claim, of course, and this is not the time or the place to go into it. But I will claim that the same thing holds with computer languages. The computer languages encourage you to think in specific ways, and I'll go further and I'll say that in my experience, R is an excellent language for statistical thinking. It encourages you to think in constructive ways about the process of statistical analysis. Having said that, I'm going to leave that hanging like a great big claim and come back to it later on. So, when you do R, you do good thinking. So, let's start with the basics. I start with reading some data into R. And here we go straight away on one of the topics that is so rarely considered when people are looking at how to sell their statistical package. Is, I don't care how well your statistical package works with your special data set that's in the examples file on my computer that you preloaded, okay? That's not interesting to me. I've got my own data, my dirty data. I want to know what your environment does with my data. So here's my data. You can just get this, type this URL in as an address, and you can tell R, read this, it's a CSV file. This is the address, okay, so I declare this variable and I read it in using the CSV file and it just reads the data from the web. So give it a URL as a string, it says, oh, you must mean that I should go get those data, and it just doesn't. Of course, if you meant they made it password protected, and there could be wrinkles like that, but we'll pass by it. So that's an easy way to get some data into your system. Of course, it's my prepackaged data, not your prepackaged data, but what can we do? So now we ask, well, what is the structure of this data set? And it tells us important things about the data set. It tells us it is a data frame, which you can think of in broadest possible terms as being a two-dimensional object where observations correspond to rows and variables correspond with columns. You can make data frames that are more complicated than that, but it's generally a bad idea because it's just confusing. We have, let's see, 7 variables in our data frame. It tells us what the names are. It tells us what the data types are. It gives us the first couple of values of each one. So, by using the str function, I see straight away, well, what kind of data am I? I'll tell you, by the way, these are forestry data. Now what I want to do is I want to see, well, how many of these data contain missing values. Now, one of the things that's nice about R is it has a mature and baked-in way of handling missing values. A missing value defined as a measurement that should be there but is not. It's not 0, it's not -9999, thank you very much. It's missing. And you need a way not only to handle these missing values, but you need a way to propagate them appropriately. Because if you don't propagate these missing values appropriately, then they get mishandled. Let me give you an example. This exact data set, in fact, source of some embarrassment as well as pride. We have measurements on trees. These are the diameters of the trees, and these are the heights of the trees. And not all the trees had their heights measured. Thinking about it for a moment, just think about it in your minds. It's much easier to measure the diameter of a tree than it is to measure the height of a tree. Consequently, commonly, heights are subsampled. We don't collect them for all the trees. And for the 15 years that I used this database, I always assumed that the heights were missing at random. And so I just said, yeah, just do whatever. R, just do whatever you want to with these missing values. You can ignore them, you can toss them out, you can average over them, whatever the heck, do whatever you like. Well, one day I was thinking, you know, I really need to fit a model. I really need to fit a generalized linear model with a binary outcome. Where can I find some data? Oh, I'll just check to see that these are missing at random. Turns out that they were not. They were not missing at random. It turns out that certain species were more likely to be measured than other species, and certain sizes of trees were more likely to be measured than other sizes of trees. So my assumption of missing at completely at random was inaccurate. So I had to change some of my notes as a consequence of that. Anyway, the point I want to make is that the missingness really matters. And R provides a mature missingness mechanism that allows you to grapple with this in a reasonable way. So what I've done here is I've asked how many of these values are missing. What I've done, this is a little bit of R foo here. I'm doing this by saying I want to run this particular function on each of the variables. I'm saying sum, whether or not the value is missing or not, from something called x, and I'm calling it on this data frame. So what it's doing is it's taking the data frame, treating it as a list, come back to those, and one at a time, it's taking these variables and saying, which ones of these are missing? So that if it's missing, it gives you a 1, if it's not missing, it gives you a 0. And then it sums those values. And we see here that it produces this list, or produces a vector with all of the names appropriately laid out and no missing values, which is happy news. I don't know whether I should suggest questions now or not. What do you think? Questions during the code time? There's a nodding. People are sick of me already. Yeah, I'm seeing a vibe. Are there any questions?
Everything's perfect.
Get that man a Coca-Cola. Here's another way to get some data. I'm going to spend some more time with these data. What we're going to do is I'm going to install a particular package called KernLab. So I install this package, I extend the functionality of R by adding packages. I install this by adding KernLab, and I add it from the repository at the University of Melbourne. Oh, by the way, all these notes will be available to anybody who wants them. So please, I know you're all writing them down frantically, but it's okay. Now I call the library into my session, and I ask for the data, and I ask for the dimensions of the data, 4,601 rows and 58 columns. I'm getting all choked up about it actually. I've chosen a particular seed because I'm about to do something that's random, so I'm setting a random seed, and I'm sampling from the values 0 to 1, where I'm asking for the number of values to be the same as the number of rows of the span data, and I want R to sample with replacement. And then I'm going to split this into training and testing data. So what I've got is I've got the span data from this kernel lab package, and I'm going to split those up into 2 data sets, one of which will be training, the other of which will be testing. And now I'm going to just do this little thing down here, which seems mysterious, but I'll explain it in a moment fully. I'm creating an empty list, which I'm calling Spangle.Models. Now what I'm going to do is I'm going to fit a bunch of models to these data. The SPAN data set is a relatively well-known data set where we have a bunch of emails, some of which are spam, some of which are not, and a bunch of predictive variables about the spam that say, well, does the word fantastic appear in the email? Or is it all in caps? Or does it start, dear beloved? Those things tend to indicate the possibility that it's spam. Okay, and I'm going to keep all the models in this Span.Models list. So, first of all, I'm going to use Fisher discriminant analysis, which is essentially linear discriminant analysis. I call the appropriate library in R, and then I'm making a new element in this list, the Span.Models list. I'm calling it FDA. This is a way to do that. And I'm assigning to it the value of the output of the FDA function, where the response variable is the type, whether the mail is spam or not spam, and everything else is the predictive variable, and that's something like 50 values. So it's much nicer just to use the dot to say use everything than to put in another 50 values. And I wanted to use the spam data, and I wanted to take a subset of the spam data and only use the training data. Okay? Now I'm going to take a brief pause because I know some of you have not used R before because you were very honest. Is that confusing? Or is it okay? Or okay. Excellent. Thank you. Okay. So that's Fisher. That's a way to fit a Fisher discriminant analysis that tries to determine whether or not an email is spam based on the occurrence of various values inside the email. Words, not values. What if I wanted to do a support vector machine instead? Well, I would call the appropriate library. There are several that do SVM, but my favorite is E1071 for no good reason other than that I know it. And I'm adding to the spam models list again a new element. I'm calling it SVM. And here is the function called support vector machine. Again, type is the response variable. Everything else is the predictive variable. From the spam data, the subset should be the training data. It's just that simple. It's just that small. I'm going to channel Steve Jobs. Could you do it any faster? Could you do it any simpler? I think not. How much would that be worth to you? What about a random forest? I'm going to do a random forest. I call the library for random forest. This is getting tedious, isn't it? And then I make a new element of the list. The list, spam models list is called random forest. I call random forest, and this looks familiar. We've seen that before. You know what that means. So now I've fitted 3 models. I fitted 3 models, and the outputs of these models are now stored as elements of the list called Span.Models. Why have I gone to these lengths? Well, my friends, I can obtain predictions for these things. Now I want to say, let's predict whether the emails that I didn't use in the model are spam or not spam. Okay, so I withheld some data, I fitted a model, and now I'm saying with the withheld data, I wish to test my model in a sort of intuitive way. I don't care about p-values, I don't care about confidence intervals. I want something that's going to tell me something about the data. So here's how we could do it. We can use the predict function. We predict the fitted model, that's it right there. I'm going to save the predictions in an object called fda.hat. And just to see what they look like, I'm going to take a table of those things. There they are. I have non-spam, 3050, and spam, 1551. These are the predictions of the data that were withheld from the fitting process. So it's out of bag. That's cool stuff. But I can use that single call, that predict call. It's the same for all 3 models. Have a question? Oh, it doesn't yet. Good question. That's just getting a prediction. No, that's a very good question. Sorry. This is just prediction for the values that we used. My apologies. Thank you. Now, if I want to actually use the prediction for the different, for the withheld data, I pass the new data argument. New data equals spam test. So it says, I'm going to go get the test data from spam. I'm going to predict these models for it. And I've wrapped this call, which is the same as this one, except that I've added the argument. I'm going to wrap this call in lapply. And what lapply does is it says, hey, you've given me a list. I'll apply this function to each element of the list. Much as a loop would. But, and honestly, no faster than a loop would, but slightly more elegantly. Slightly more pleasingly. So I'm applying my prediction function, which has the same structure, to each of the models that are stored in the spam.models list. Saving those outputs in something called spam.hats, which is also a list. And if I were bored, if I were tired, if this were tedious, instead of using lapply, I could call parallel library and use mclapply, which has only one more argument, and that is, how many cores would you like me to use while I do this? How many cores? Now, I'm just running with a little Mac laptop, so I said 4 cores, please. Because if I said more than that, it'd say, screw you. But at the university, you know, we've got some bigger machines. We've got some machines that have more cores than 4. So you can get a bit of a speed up. But actually, so honestly, really the difference between the previous call and this call wasn't very much. But it does hammer home the point, I think, that going from single core to multi-core on problems that are easily generalized is relatively straightforward. Okay, so now I can use the lapply, which, remember, takes a function and applies it to elements of a list, and I can say, tell me how many of these predictions are spam. When for the FDA model, 766 of the predictions were spam. For the SVM model, 858 of the predictions were spam, and for random forest, 862 were spam. So straight away we see some differentiation between how these models have tackled the problem. What about if I want to make a table? Well, I can use my lapply again. Those of you, by the way, who are familiar with programming may recognize these functions I'm writing as lambdas. I'm not giving them any names, I'm just saying, hey, create a function temporarily and destroy it. Doesn't give it a name. So, this time I want you to table the data, and I want you to take the predicted and the actual from the original data set. So now we have crosstabs of the predictions. The FDA crosstab looks like that. I won't read out the numbers. The SVM crosstab looks like this, and the random forest crosstab looks like this. Each of them with the same structure. And what I'm doing here is I'm just saying, hey, let's have the actual counts on the columns and the predicted counts on the rows. So a quick interpretation, for example, support vector machine, where there was predicted non-spam, actually non-spam was 1301, and spam was 86. Where there was predicted spam, the non-spam was 58, and the spam was 800. So now we're getting closer to saying, well, what has this model actually done? Remember, these are out-of-bag data. These are data that were withheld from the model fitting process. Okay, and we're just covering this off against all 3 of the models that are held inside my list using the lapply function. Yes?
Can you explain about the figures again?
Yes, I can. They are cross-tabulations of the predicted against the actual status of the observations that were withheld from the data. So for each observation that was withheld, we know whether it was predicted to be spam or not spam, and whether it was spam or not spam. So now this tells us that of the articles that were predicted to not be spammed by FDA, 1,302 of them were not spammed. This is the truth up here, and 177 of them were spammed. So it's like a confusion matrix.
So 177 were predicted, like false predictions in case of non-spam.
Yes, that's right. Of course, I don't have to use functions that I write. I can grab anyone's functions as long as I trust them. It seems to me that using something like the odds ratio is probably a little bit more of a compact way to summarize the quality of this model. So I've grabbed somebody's odds ratio procedure, and I'm applying it here inside LPY, and once again, we get the answer sort of model by model. FDA odds ratio is 92. The support effective machine's odds ratio is 208, 209. Random forest is 423. And there's a little bit of overlap between the estimated confidence intervals of the support effective machine and the random forest, but the overlap is very small. I haven't done a formal test here to say which of the three techniques would you use if you were to be trying to predict spam, but I would lean towards the random forest personally, with the odds ratio being 423 with a lower confidence interval of 280 and an upper confidence interval of 630. 95% confidence interval, I should say. Okay, so what we've got then is I fitted three models by three different techniques to the same data set, and then just using LApply, I was able to pull out important statistics that were presented in the form of a list with named elements for easy comparison. And there were no smoke and mirrors. You saw all the code necessary to do that. Questions? For these particular data, I've already wiped out the missing values. So the anecdote, they didn't exactly relate to the anecdote. Okay, so what else can we do with R? I'm grabbing another data set. This is the data set that I already had in my computer, but it's available on my website if anybody wants to use it. It's the stage data. What stage data? The stage data are is a data set from the early 1960s, where a colleague of mine felled around 60 grand fir trees in 9 national forests around the state of Idaho, and he cut them down and then he cut them up the middle and measured the diameter and height growth every decade. So we have decadal height and diameter measurements of these 67 odd trees. They came from, as I said, 9 national forests, and in the national forests there were different kinds of growth opportunities for the trees, I guess is a nice way to say it. Different kinds of soil conditions, different kinds of moisture availability, and so on and so forth. And we're going to refer to these as habitat types. And the habitat types are flagged by the dominant vegetation. That's these values here. So this is just some R stuff. You don't have to worry about it. If you want to know about it, then you can grab the presentation. What I want to talk about now is printing and plotting. Now there's a particular package that's come up in, recently become more popular in R called ggplot2. It's based on the idea of the grammar of graphics. It's written by a chap called Hadley. Hands up here who uses ggplot2. Pretty good group. I resisted ggplot2 for many years because I found the syntax confusing, but I suspect that's just because I had spent many years doing something else altogether. It turns out that if you just start with this stuff, it's actually pretty easy. So I'm just going to do a plot of the diameter against the height of the stage data. Okay, that's what this code is doing. Here's what it looks like. Diameter, height, and each point is a measurement. Well, what do we see? What do we see there? Give me a Gestalt kind of feel for those data. Opinions. There's a linear relationship. Yeah. Yes, I agree with that. Does anything make you suspicious? Excuse me? then it does disperse towards the middle, and then it narrows. That's kind of odd. It's rare. There could be some species. It's all one species. That's a good conjecture. That's a good conjecture there. One of the things that worries me about it is this almost regular set of points here, and this almost regular set of points here. I wonder what those could be. So I'm going to change the plot by adding a line instruction and tell to group these by tree. These are multiple measurements per tree. So if I say, hey, make each tree into a line, then this is what R produces. And we can see that this group of points that have irked me are all measures on a single tree. Likewise, these ones down here. And we get some explanation for the dispersal towards the middle and then the sort of lessening dispersal towards the upper end. There's a correlation between the measurements within the tree, within the trees. Okay, but what about if I wanted to distinguish between the habitat types of the trees? Remember those dominant vegetation classes? It turns out that there's sort of 5 different vegetation classes. Each of these indexes a separate kind of growing potential for the trees. So we can identify these areas as having low or high potential for the growth of the trees, and we identify those by their dominant vegetation. I don't want to go into too much more detail on that, but is that sort of kind of satisfactory? Yeah, it seems biologically plausible. So here's what that graph produces, what that code produces. Now the tree lines are coloured by the habitat type from which they came. Now I didn't have to ask R to produce the legend. The legend came out of the box. Okay, so we can go a little bit further. We can say, what about if I want to see what effect this has on, the National Forest has on this? So I'm now adding a faceting command by forest ID. And just adding that command changes the graph to look like this. Now we have each national forest delineated and trees separated by national forest, still coloured by habitat type, but coloured consistently within the national forest. This tells us, this provides us with an extremely succinct summary of the structure of the data. We've got trees, the trajectory of trees, we've got them coloured by their habitat, we've got them organised by their national forest, and again, the x value is the diameter of the tree, the y value is the height, and now we see that despite our early conjecture that there was kind of a linear relationship between the diameter and the height, actually for many of the trees there is some sort of curvature which was disguised in the original data set. But it did create that illusion of thickening in the middle and thinning at the ends. Questions? Hello? So, are you thinking of any packages in particular?
Yes, I was working on PCA and then we kept going with packages. And so one of them was cycle subset, and this one I was very happy with in terms of the ability to check all the calculus. But with the other that was offered, I found references, I wasn't happy with the result that I saw.
Okay. Let me generalize that point a little bit because it's a really important one. It's one that I promised in my mind to come back to, but I forgot. So rather than, I'd like to address the point of plotting perhaps afterwards, one-on-one, but the more broad point is that R is extended by the use of packages, and the R universe comprises many packages, and they don't all do the same thing, and what they do, they don't all do equally well. Consequently, there's a really strong buyer beware atmosphere surrounding the use of these extending packages. Now honestly, there's a buyer beware atmosphere surrounding any software product. Anything you use, if you need to do some due diligence with. And that means use it on your own data where you know what you think is going to happen, or examine the source code, or both. The obligation is on you to be sure that the product does what you think it will do. Now, there are different mechanisms for resolving conflicts that I won't go into. But the point about it is, different packages will behave differently, and you need to figure out which one does the things you want to do and does them best. And I'll pick up the specifics of that topic later on if I could. Yes?
How customizable is it in terms of select
Highly. Highly customizable. Yeah, you can say, give me these 3 colors, and you can give them by name, or you can give them by RGB, or whatever. There's a lot of it's easy to articulate. Yeah. Okay, so there's 2 examples of R stuff. The first one was I fitted some models using the span data. The second one was I did some plotting. The third one, I want to take you on a relatively quick journey when I was puzzling about something online. Now, I am an avid gamer. I really enjoy computer games. They make me very, nearly as happy as R makes me. And I was looking at there's a gaming site called Metacritic that not only reviews and overviews games, but also other products as well. And there's here's a list of the best games of all time. What Metacritic does is it aggregates reviews from various sources, and then it produces an overview, a sort of single statistical value that supposedly represents the quality of the game. So, hands up to all gamers here. Gamers, be proud, come on. Come on, I see some reluctance. Thank you very much. Who's played Half-Life 2? Yeah, there we go. That's right. Thank you very much. Top game in history, for the PC I should add, Half-Life 2. Second top game, Out of the Park Baseball, 2007. Now, those of you who are not gamers will not necessarily see this as anomalous. But this is really a niche game, my friends. No gaming list that has Half-Life 2 and Half-Life and the orange box, which has Half-Life in it, and Bioshock and Portal 2. No list. This doesn't belong in the same list. And we can see a clue or a hint about this in the user reviews, which are way down at 2.6, whereas everything else is way above 8. So I was offended, my friends. I was offended by this, and I thought, how can they do this? I want to figure out what they've done. So I wrote an R script that scraped Metacritic. So I thought it would be fun to share with you, not the script itself, although I'm happy to share with anyone who wants it, but rather the process that R enabled me to do. And that was, I could get all of the reviews of all of the games from Metacritic using R, because it can read HTML, and pick out the appropriate pieces, and then reconstruct my own, much better ranking. What I need to do, I need a list of all the games, and I need tags, years, and the nominal scores. And those are actually all on the main page, except the tags, which I grabbed another way. And then for each game, I wanted to obtain the journal ID and the score for each journal. For some of these games, they had like 100 scores. So for those games, I wanted to grab those 100 scores and those 100 journal IDs. Okay? And then I had to merge these data sets. And so I used these functions, wget, paste, scan, grep, substring, and merge, in order to obtain those. So that grabs the data. And then I fit a statistical model. I made the response variable be the journal score for the game, and the game I made to be a random predictor. This is a mixed effects block, a thing of vast beauty. And then journal, also I made a random predictor. I'm not going to go into the theory of mixed effects models, but this is a way of trying to accommodate the variation without necessarily bending to it entirely. And then I could extract the statistics. From this model, the game estimate was the new score, the within-game standard deviation could be a measure of the controversy. I've got a particular game effect. The game has like 100 journal scores. If the standard deviation of those journal scores is high, then the game is controversial. If the standard deviation is low, the game is not controversial. I grab the journal estimates. If the journal effect was high, then the journal was an optimistic journal. If the journal effect was low, then they were a more less optimistic journal. And then within journal standard deviation, because of course I can grab that estimate, was a measure of discernment in the units of the data. So I could identify which journals had the highest variance. These would be the journals that you would trust to be discerning. Some journals give everything 8 to 10 out of 10. Well, who cares what they think? Some journals give you anywhere between 3 and 9. Now, they're the journals that I want to read. And to obtain these beautiful statistics, I use the L and the R function and the predict and got estimates of the fixed effects. So here's the new top 20. Half-Life 2 remains justifiably at the top. And Out of the Park Baseball, still a fine effort. It's all the way down here. Why did it shrink so far? It was based on 5 reviews. Okay, Half-Life 2 is based on 81 reviews. It doesn't seem reasonable to me that if 5 journals measure a niche game, then they all say, oh, this is a good game. That would have the same weight, in my mind, as the glory of Half-Life 2. Command and Conquer is... Oh, it disappeared altogether. I'm sad to say. Command and Conquer is old school, and it was only actually assessed by a small number of journals. So it was not a small sample size problem. Yeah, I was sad about that. Here are the most controversial games. Let me see if there's any that I actually recognize. Supreme Commander 2, I have that now. Highly controversial, 30 journals. The standard deviation was 26. So this is a score from 0 to 100. The standard deviation is 26. So the 95% confidence interval, if we assume normality, the 95% prediction interval, I should say, is plus or minus 50. This suggests that Supreme Commander 2 obtains scores anywhere from 0 to 100, which I think it actually did. The most discerning 15 publications, here's my favorite, AV Club for the Onion. These have the highest variation. The variation of the Onion, standard deviation is 25. So the Onion, with an average of 74, will give you results anywhere from 30 to 100. So if you really want to know what's going on in games, read the Onion. It's also very entertaining. Okay, so what else can I read remote files, which I showed you earlier. It pipes, it speaks neurometeorology, it speaks Twitter, R speaks Google Viz, and R speaks Google Docs. You can see I'm picking up, right? We're nearly there. You've been fabulous. Your patience is extraordinary. So one of the accusations that is unfairly leveled at R is that R is slow. Well, yes, actually that's true. R is true, but that's a value judgment. And I'm a scientist, goddammit. I have no time for value judgments. If you want to speed R up, well, hold on, before I jump into a solution for a problem that doesn't really exist. You've got to look at the whole package. You can't just look at how fast does R execute commands. You have to look at how fast am I plus R, not how fast is R. How fast am I plus R? I don't know if you can see the script here. It's kind of faint. I'm not going to read it out. It's a C++ script. What R lets you do is it lets you write C++ scripts in line and then compile them with just a function call and then call them. So if R is getting on your wick because you think it's a little slow, my friends, drop into C++, solve your problem, if that's what you need to out. And for simulations, I've had to do this a number of times. For simulations, code it in R, get a rapid template going, make sure I understand what's happening, drop into C++ and speed things up 100-fold or more. There's I was doing a number of years ago. I was working on a statistical problem about trees, and I had a lot of trees in my database. At 64,000. I know with you big data guys, you're saying, ho-hum, that's a lot of measurements. You wouldn't say ho-hum if you had to measure 64,000. And the statistic that I was calculating required a triple loop across the data. And I was doing this by species, and the most common species was about 30,000. A triple loop across 30,000 observations is somewhere in the trillions of operations. Triple loop in the trillions. So I set up my R script to run this, and I was I put it on my server. I was in a different city at the time, so I was logging in and using Screen and checking it out and watching it run. And after the first day, it had done 0.1 of 1% of the needed operations. So I thought, okay, this is going to take the year, right? Assuming that my computer even stays up that long. So the next day, I gave up on that. I rewrote the triple loop in C, and it took 3 hours to run the whole thing. So, okay, R really can be slow, but there really is an easy remedy. Drop into C and speed it up 10,000-fold. And code smarter. I'm not that great at code. Anyway, so for those of you who would like to try C++ written in R, that's what it looks like. And it works. The sum of all the integers from 1 to 10 million took about 2 seconds. Maybe even a little less. Okay, so that's my plus R. And now I'm going to talk about not R. R can't do everything. R is brutal and will not hold your hand. R is not gentle. The documentation has been written by a committee who hated each other. I don't think I need to say anything more about it. The documentation is uniform, is not uniformly terrible, it's variably terrible. Sometimes it's awesome, and sometimes it's not awesome. And the standards change. This makes me weep. You remember the missing values I told you about that R handles responsibly? Well, it turns out that you want to do different things with missing values, but it turns also out that most of these functions, the way to tell them what to do with the missing values is not the same. Sometimes it's na.rm equals something. Sometimes it's na equals something. Sometimes it's narm equals something. And you have to remember or you have to look it up. I am an inveterate look-it-upper. Despite the fact that I've been using R for R and its antecedents for nearly 20 years, I still Google every day. I don't know whether that's a comment about me, my code, or R, but I Google every day to solve little problems. R can drive you crazy because of these different standards. I've had people, I do workshops. I used to do workshops in R. I've had grown people in tears in my workshop because R is so fucking stupid. Do you want to bleep that for YouTube? The packages are unreliably tested. Some of the packages have been used by thousands of people thousands of times. Some of the packages were written by idiots like me and have been used by idiots like me. And you don't know which is which until you find out whether you're an idiot or not. So you've got to check. But okay, big footnote. Even SAS has to be checked. You can't trust anyone. Okay. R stores object in RAM. That's very efficient for processing. It's not very smart if you want to have big objects. This is not strictly entirely 100% true anymore. It turns out that people have written packages that allow you to do manipulations on data objects that are stored on your hard drive. They're not super fast compared with other things, but they do let you manipulate arbitrarily large data sets. R doesn't really have a GUI, although that's less true with RStudio. Users of RStudio? Yeah, it's pretty slick. It's a little slow on my Mac, otherwise I would use it, but I'm an Emacs person. And that's, you know, I sacrificed goats to learn Emacs. I'm not going to let that go. R is not the fastest thing, R is actually, you know, it's not fast and slow. But if you really need speed, drop it to C or C++. But the important thing is to remember, what do you like when you add yourself to R? It's not just R by itself. It's you or the people you work with plus R. Sorting, this is an embarrassing thing. Sorting is platform specific. So it turns out that platforms specify the orders of certain things. So if you do sorting, if you sort vectors, I'm thinking about capital letters here. If you sort these on one platform and you're not careful about how you communicate that sorting, you can get a different order when you run that same code on another platform. And that sucks. Especially when your platform is your development platform and your client's platform is the other platform. And the little sorting comes up wrong and you look like an idiot. That has happened. And R doesn't do native parallelization. We can do embarrassingly parallel stuff like I showed you before, where we split things among cores. That's easy to do. But R can't take single objects and split those amongst cores, and it probably won't be able to do it because R is single threaded. And there's no, I don't believe that there is any substantial undertaking to try to make R multi-threaded natively.
Yeah, actually, I recently know that R is acquired by Microsoft.
No, my friend. No, there is a variation of R that is a commercial product called Revolution R that has been acquired by Microsoft. Bless their copper socks. But that is I don't use R when I could use a spreadsheet to look at things. You have a spreadsheet's a great way of just getting a quick gestalt look at a small data set. And R sucks at that. Because sometimes you just want to look at the numbers. You just want to look at the rows, you want to look at the columns, you just want to scan things with your eyes. And spreadsheets do that much better than R does. So I don't eyeball in R. What are your options? You could use, I could SAS up top. SAS, you could use SAS. You could use Stata, you could use Octave, you could use Python, which would require Psyche or NumPy, and other stuff that Chris is going to tell us about. You could use Julia, or you could use Excel. You could use some of these things to analyze data, but it wouldn't be as fun. It wouldn't be as beautiful. It wouldn't be as good. You could use numeric instead of Excel. Excel's not the only spreadsheet. So, so now I get to get off that soapbox and onto my other soapbox. Yes? Before my six.
Would you like to add SPS instead?
Would I like to? I would love to. I could do it right now. SPSS.
How effective is to use R in Hadoop environments to scale the processing?
Yes. We'll play with Hadoop for scaling. I haven't tried that myself because I haven't tackled the kinds of problems that demand it, but I understand that it is doable and not too painful, for what that's worth.
Especially like those kind of tree loops that you explained before.
Yes.
You can actually put into a complete whole step up MapReduce environment, and you can actually, of course, as you said, C is much better. But
Yes.
in case if there is no other option, you can actually use MapReduce environment to split the jobs.
Yes. That is true. That is true. Absolutely true. I'll say it loudly because you're a softly spoken, intelligent man. The point has been made that R does communicate with Hadoop nicely. So if you have large-scale problems that require large-scale iron, you can split them up using Hadoop and MapReduce, and R will control all that good stuff for you. Thank you.
Question.
Oh, yes. So,
You obviously follow R much more than I do. Where do you think this other block development around parallelism for R, not vertical and horizontal scaling, where do you think that's, what's good work now, where do you think that's going to go?
I don't know. I'm in a very fortunate situation that if I can't program myself out of a problem, I'll buy myself out of a problem. At least that works for the kinds of problems that I tackle.
When you're dealing with millions of data,
So I think most of the work that R will end up using is going on outside R. really what we're probably looking at is developments like Hadoop that will handle stuff that R will then reach into and curate. But I don't think R is going to change sufficiently that it can handle the big iron problems that we tackle natively. So I think look outside R for that innovation, but look to R to soak it up. That's my guess. Okay, my last soapbox. You've been exceptionally patient. I love you all. So my opinion is, I just made this number up, for 95% of programming problems, the best language is the one that you're best at. If you're good at R, use R. If you're good at Python, use Python, because U plus whatever you're good at will be quicker than U plus something else a whole lot of the time. But if you're a beginner, then you should be promiscuous. You should try lots of languages. And ideally, you should try languages that have distinct characteristics so that you can get a sense of the spread of the potential of languages. So there's R, but R is a procedural language. So go for something, if you want to couple something with R, go for something that's compilable. Or like C, for example, or C++. So the point I'm making here is that the argument or the question about should you learn R or should you learn Python is kind of a smoke screen. Honestly, you could probably learn either of them, and a smart person is going to do very well with both of them. As much as anything, it's probably going to come down to flavor. But try lots of things. Try lots of different things. Because everything is going to drive you wild once in a while. And it's good to find out in exactly what way what you're using will drive you crazy before you sink too much time into it.
Speaking of things that drive people crazy, when you work with Python, you look up different ways of doing things online. There's often reference to a Pythonic way of doing things, which is, I guess it boils down to the culture of
those fascists. How do you like that?
So, on the flip side, it is a value of common idea, things like that people have figured out work well. So, do you see that kind of, common idioms and R way of doing things?
Yes. My way is the R way. That's a great question. Let me come back to that. Okay? I will come back to it. Let me finish.
Oh, it's true.
Question. Look, I thought I'd ask R. R or not R? Thank you, R. So now to come to that excellent question, is there an R way of doing things? There absolutely is. Let me grab some of my code back here, because it's a good example of beautiful R. Oh yeah, I say that, right? Of course I say that. Where are we headed? Back to... Yeah, all the way up here. Lots of people who are starting R will say, what's with the little arrow things? You could use equals, couldn't you? And the answer is, yeah, you could. But there are certain circumstances under which the equals is a little bit ambiguous. And they would say, well, how often does that happen? You say, well, never. But I'm old-fashioned, right? For me, the arrows are soothing. And I'm willing, and I use Emacs as I mentioned before, and that's just control underscore. And I'm willing to do the control underscore instead of the equal sign in order to make my code soothing. So yes, there are R ways of doing things. Another example is this little S-apply thing here with the lambda. That's kind of R-y. Just inventing a little function will do the trick. It's all, it's R, I call it R-y, but honestly it's more Unixy. It's like take these tools, put them together, and make them do something. Don't write a function that finds all the missing values in a function, because there's no point. Don't write that function, be Unixy. Build these things out of smaller components. Where's another example of my beautiful code? I had another one. No, I didn't. That's it. Yeah, so the answer is yes. But we're not really very prescriptive. Use the arrow sign. Oh, there is. Of course there is. I'm so sorry. The whole S-apply deal, instead of using a loop. There we go. So I could have looped through each of these things. I could have written a loop this. I'd create a container, and I would say for I in 1 to 7, grab the column and do the thing. But instead of doing the whole loopy thing, I did S-apply. So that, it still creates a loop. It's sugar, right? It's just an interface. But that is a kind of R-y way to try to do things. It's an illusion as much as anything that relies on a history with S+. It turns out that back in the day, and when I say back in the day, I mean 25 years ago, S+ had a really inefficient looping model. And you could run out of memory and things could blow up. So people really focused on not doing loops. And that kind of cultural idea has bled into R, not even necessarily, because R's looping is much more efficient than it was before. But people will still say, if you can avoid a loop, it's a good idea to avoid a loop. But honestly, not with much justification. I'll take more questions. So,
Have you ever used MATLAB for more than 1 year?
have I ever used MATLAB for more than 1 year? I blush to confess that the first thing I do when I get a MATLAB script is translate it into R. So the answer to the question is no, I'm the guilty son. Never used MATLAB. So.
Actually, another question. I would like to have a request for influential people in the art community. Maybe Grand and some other sites look a bit nicer. Interact with the good design folks and say, let's make it look bigger.
If only we knew people who did design. Yes, we can certainly make a committee and make a representation to the CRAN maintainers to say, could you make yourselves less ugly? And I'm sure that they would receive that request with equanimity.
So actually they don't hate each other.
Have you heard of SSH? Something of this not really.
That's it.
So a few really quick questions. So looking at meta analysis of game, did you manage any studies to learn half-life?
Sorry,
Did you manage any studies to learn half-life?
I projected it, right? Yeah, the Half-Life 3 is in the future.
There's a 3 in your data set. It's good fun.
That's right. It's got to be there somewhere.
So the next actual serious question is, has R been successfully used at a production scale with
I don't know.
early stage production?
I don't know whether it's been successfully used in a production setting with GPUs. The answer-
And it managed for our statistical analysis of the audio. Has that actually been to the domains?
I do not know. Don't know. Google might tell us. I'm not sure. That's it? Yep.
That's it, okay, so we'll leave. So we're going to have a 5-minute break now, and round 2 with Chris, and then we're going to have a joint Q&A at the end. So grab a beer, have a break.